And I think that's the mission of 1000Kelvin from a sustainability perspective. We want to really hammer that message so that even engineers who are not generally connected to the, I don't want to say not all of them, but we don't think about sustainability when we make our decision. We think about productivity, cost, success. And I think this is something we want to integrate to that decision-making process. I'm actually one of the co-founders of 1000Kelvin. Started actually in AM already more than 10 years ago. After graduating from Georgia Tech, I went to a first job in the oil and gas industry in the Houston area, where I was one of the first engineers to witness the capabilities of AM, but also the limitations. The promise at that time was massive for oil and gas companies, like distributed manufacturing, printing complex geometries, but it was really quite early. And as I have been actually doing a lot of academic work on residual stresses, which is one of the devils behind the issues in AM, I was like, that's really cool. I found a process that justifies all my lengthy academic career, so I'm going to stick to it. And actually, as a matter of fact, I had the opportunity to move to Germany from Texas and join Siemens. And Siemens at that time, as you know, really large conglomerate, and I wanted to focus on AM and joined the first team building software for additive manufacturing. It was a great experience. I was product manager actually for the first process simulation, which is using simulation technology to predict these issues. Again, sticking to my expertise. But what was interesting in this experience is how much I realized that using simulation technology was not so much adapted to manufacturing floors. And, you know, these people are in the speed and the production. The objective is to make a part, not to analyze it. And I realized quickly that the technology, although great, provided huge insight and a lot of knowledge, was not really adapted to that. I continued actually at Siemens for a few years, being in charge of the whole build preparation software. Then after that, I was more in the business unit. And I got scared a little bit. I moved to the semiconductor. I thought maybe I don't want to spend all my life in AM. I need to see something else. And then once I moved to the semiconductor, it's a great company called, owned now by MKS Instrument, active in the semiconductor, where I was in charge of a small unit developing digital solutions for our equipment. I realized how AM was just not yet an industry, how it was not really born yet compared to semiconductor, and how the CEOs of these companies we worked with looked at the yield, and you know, all these KPIs were like extremely important for them. And then I called some of my friends, my co-founder actually at Siemens, who was a brilliant quantum physicist and was doing research on simulation. And I told her, well, you know what, I think AM really is not born yet, and it's really great opportunity to be there and solve the problems. And that's how we started, Katarina and myself, 1000Kelvin, already 3 years ago. And what we do in essence is trying to build technology based on AI, deep learning surrogate models, that really is a co-pilot. So what does that mean? We try to take all these complex physics challenges that are happening in the AM process, predict them precisely, and try to solve them upfront and help the engineer be more successful. Because one of the biggest challenges in AM today is everyone thinks it's just like I take my design and I print it. Actually, as you know, you need really advanced engineers, capable people, tons of failure history and experience to make it work. As a friend of mine from a large OEM says, our machines are either going to be driven by an AI that doesn't exist. Meanwhile, if you want to run these machines, you need a Michael Schumacher to operate them. So we are building that Michael Schumacher of a pilot. So the company now is 10 people. We are both in Berlin and LA. We are serving multiple industries, and we're working on a really complex problem with the top companies and trying to solve these issues of repeatability, failure, scrap, you know, all these issues that are really complex in AM today. And we are happy to be already on the market and helping these people.
So, quick question: why 1000 Kelvin?
Oh, that's a hot question. So we're mainly physics team. Most of my team have PhDs in physics, and obviously what we do is physics informed machine learning technologies, where we try to capture the physics and train these algorithms. And then quickly we realized that thermal management is one we want to solve, and we were looking at how mechanical engineers are solving the problem today. And most of mechanical engineers, and I'm mechanical engineers, we're trained on a not so advanced understanding of heat transfer. We think more conduction, there is heat and it will conduct. But physicists always respect all the heat transfer modes. And at 1000 Kelvin specifically, there is something that happens where radiation becomes as important as other heat transfer modes. And it's very difficult to capture radiation. So it was to tease people into, don't try to understand it too much. Let's actually physics and advanced computational models capture the phenomena for you. They say our product is called AMAIZE, so that we don't bother people with too much of 1000 Kelvin.
Okay, fair enough. And AMAIZE being AMAIZE, so you've got the additive manufacturing, the artificial intelligence.
Oh man. But that the true history behind AMAIZE is, whenever I used to do the first demos, and the AI Copilot was not really hot at that time, because it was released only after we have released. Everyone was like, "Oh, this is amazing! Oh, this is amazing!" Because it's really so easy for engineers. Like, they could see that we are capturing the problem, providing solutions, solving it, and of course they are like, "Oh, finally someone listened to us and bring in a solution." So it's a mix of both, to be honest.
A backronym, I think they call it.
A backronym, that's a good one. I'll take note of that. Backronym.
So how would an engineer integrate the AMAIZE product into their workflow? Where does it fit in and start and end for them?
Yeah. So most of engineers today, and the way I think about engineering starts in the PLM, in the design. Companies are not there to become experts in AM. Companies are there to innovate and build advanced product that solves important issues in society. And they are focusing on the specificity of the product and the functions. And they just want to print it. And printing is just a decision to produce the part. It can be machining, it can be other processes. But the moment they go to the 3D printing, they realize they need so many tools, so many software, so many capabilities, knowledge, education, and it becomes really a blocker. So the philosophy of our product was really to look at this sophisticated workflow and to think for the engineers, how can we make that streamlined and easy for them? And the way we do it today is to say, you know what, just take your part, do your whatever you need to do in terms of build nesting and build preparation. And we know that you are scared from printing it because it might fail and you have to do it again. And so give us that last file, the G code, the recipe. We will analyze it using our AI, and we will show you where the issues are, and we will propose to you multiple corrections so you have always control. And we will apply the correction you want, and then we will send it in a natively integrated manner to the machine. So we work hand in hand with OEMs to make that workflow extremely easy for them. And this is how we serve our customer community today. Obviously, we have other ideas to expand and make it easier even earlier in the process. But I think, given the pressure most of our customers have today, we're already solving a big pain for them.
And is it fairly easy to get the information that you need from the OEMs to put in at the start of the process and for the export and the actual building? Yeah.
I think OEMs have they're in this industry for a long time. They understand exactly what's blocking the industry from scaling. They know that as long as engineers are not successful fast with this technology, they are not going to buy more machines. They are not going to scale. So they are really building ecosystems around their systems to enable their customers to be successful, faster, better, etc. So I wouldn't say that we had any challenge actually working with the design companies or with the OEMs. Everyone is willing to support the customers to solve the problems. As long as they believe really you have a solution and you're just not just creating more sophistication or complexity.
Yeah. Absolutely. In terms of obviously using this, one of the goals is to reduce the amount of failure rates in prints. Do you have, or have you conducted any research on what those failure rates were because of defects that could be fixed before you start the process?
Obviously, there are data out there, but I can also reflect based on our experience. We're working with different industries that are looking at different materials and different geometries. So when you look at companies in the energy sector that just want to reduce the lead time, they don't want to rethink design. They just want to take a casted part and print it. And casted parts generally are massive. They come with a lot of complexity. So these people tend to have some challenges because the parts are not designed for AM.
Yep.
So the prototyping companies are dealing with massive amounts of diverse geometries. So the engineers are struggling day to day, like they have to juggle between processes, geometries. So I would say that something between 50 to 80% would be accurate, depending on the industry.
Okay.
Or on the. However, you have to put this in a perspective. Of course, someone doing the same print every day will have a high success rate, right? But those are almost like we want more of these cases, and in order to have more of these high success rate cases, we need to start from helping people who are taking risks. So that's where we are interested in. We are not interested in those who are. And when you put this in contrast with other manufacturing processes, even those who are able to print at high consistency and repeatability, it's actually very hard to compete with processes like machining or forging or others. And when you are in these large companies who look at 3D printing just as any other manufacturing process, that's the expectation. That's what they look at us and ask us as industry to align to. And we at 1000Kelvin, we want to be part of the solution. We want to go and help the industry get to that standard of quality, repeatability, etc.
Mm-hmm. Yeah, I think as we've said before, if you're looking at additive manufacturing, the entire value chain, it really, there are a lot of places in there that people can become put off from trying to adopt it, whether that's materials choice or qualification and validation. But I mean, repeatability has been one of the industry watchwords for, I don't know, forever, since, the 80s. Can we make it more repeatable? Can we make it more reliable? Can it ever get to the point, like you say, that it can go toe-to-toe with machining? I mean, if you're machining a billet block, really there shouldn't be too many opportunities for that to go wrong in any sort of consistent manner.
Yeah.
So
but it's possible.
It is.
I think it's a tough like let's just appreciate the complexity of the challenge. Yeah. So it is a complex process. It is involving not only creating a geometry, it's also involving creating material, it's involving a lot of energy, a lot of thermal issues, a lot of stability. So I think from a physics perspective, it is complicated. However, using a systematic approach at looking at the problems and trying to solve them one after another, I think it's absolutely possible to master it.
Mm-hmm. Yeah, it does have the benefit and also the drawback of operating kind of at the edge of physics and chemistry and metallurgy. True. And all of these linked but disparate elements that makes it such a challenge. But also that is really where the benefit lies. Like you say, if you are creating the material at the same time as you are creating the part, then that obviously opens up fundamentally different opportunities for manufacturers than being faced with a block of a homogeneous material and make your part out of it.
Absolutely.
So in terms of the OEMs that you're working with, how many of the I don't know, the companies that we would have seen on the show floor at Formnext are you actively involved with at the moment?
You mean machine OEMs or?
Sorry, machine OEMs.
Okay, I think pretty much all of them we're working with, either already integrated, with companies like EOS, which I have to admit, quite impressive ecosystem around their systems. SLM also, Nikon SLM now, as well as many others in Europe, but also in Asia and the United States. So, and always the integration is not driven by, it's always driven by a use case that the customer comes to us and say, I need to use your technology. And then what systems do you have? And then we work hand in hand with the OEMs to enable them. So that's how the relationship with OEMs have been developing over the years at 1000Kelvin.
And in terms of the what impact do the materials have on the how you would use AMAIZE in your process? Presumably you have to dial in the parameters for specific materials. So if you've got the coverage of the entire, so an EOS, M400, all the materials that can be processed on that system are able to be.
So there is a good news and a bad news. The good news is for us, obviously not for the industry, is we are really not using a lot of materials in AM. When you look at the variety of existing materials that could be used in other manufacturing process, that makes it achievable for us to build these machine learning models that are material specific, as you could guess. And it is really painful. I mean, that's the hardest part. That's why I have a large physics team, and we are using extremely large computers to build these models. We need to generate more than 20 million data points, for example, just to have the first version on a specific material before we can even ship it to a customer. This said, I think, there's also something happening from a digital side. The cost of compute is dropping exponentially over the years with all these large cloud computers. There is a large workforce, especially in Europe and Germany, where we have a lot of really high quality engineers, especially well trained on machine learning. So we're benefiting from a nice ecosystem where we have the right competencies and capabilities to be able to build this complex model rather fast and in a consistent way. So we are fortunate from that perspective. As of today, we're covering pretty much the most important materials that we see. There is also demand. There's a lot of nickel alloys, a lot of stainless steel, titanium. But we're also starting to look at polymer. Obviously, I have learned through the experience of the last few years that in polymer, SLS, there are also the same challenges. So, yeah, I think for us there is definitely a massive amount of work and complexity to address to support the industry. I think that's my message, consistent message to community is like there are so many of our AM problems that could be solved with AI. And we need absolutely to look at it as an ally, not as a scary buzzword again for marketing, because we are all sensitive from marketing, as you said. But there are definitely serious solutions for us in that technology.
Yeah, I mean, I think it's a data-rich environment, and I think it lends itself to that kind of analysis and the ability to integrate AI into, from the design phase. Is more often than not, if you're designing, you have to design for the process, you have to design for manufacturability with AM, not necessarily the way that you would in any other process. So people need help with that. That's another hurdle, I guess. People are we've got our catalogue of parts that we've been injection molding or milling or whatever for the last 50 years. So we don't really want to have to start redesigning everything. But throw it into the computer and let the AI do it.
It's gonna happen.
So in terms of sustainability then, the process is or isn't sustainable depending on how deep you look into it, which process you're looking at, etc. Failure rates, as high as they are, I imagine have probably an outsized impact. And I can't remember ever talking about or hearing in a presentation at one of the many conferences when people are talking about the sustainability of the process. Yes, they talk about, there's less, you don't create buckets and buckets of swarf for every part, so there's less waste there. They don't really talk about, we had to print this 3 times and each print took 2 days and used 40 kilos of material and we had to scrap it. How big an impact do you think it can have getting those success rates up in terms of the environmental impact.
So I think you and I, we have discussed this. Obviously, there is a hierarchy of influencing parameters on calling something sustainable or not. And I think that the type of energy you're using is mainly probably a bigger driver than transportation or scrap rates. So I think it's always where are you doing your printing, etc., etc. So I'm not saying that the trial and error or scrap rate is the main driver. However, it is obviously something you want to have under control. And today in our industry, now that I put a little bit the framework, within our industry, engineers have been learning traditionally using trial and error. Forget about even the failure rate or scrap. It's just like the traditional go-to approach is, I'm going to try, we're going to learn, and we know how to do it. I think that we as a one of the first or unique digital manufacturing technologies, we must use digital technologies before we go to the systems and click on printing and try to learn on these expensive and highly energy consuming platforms. So that's really where I see us contributing. That's the message I give to engineers. Please don't print, don't do trial and error, bring all the iteration to a fully digital system. And I think that some of the direct consequences of this is obviously, you could see it on a very nice report for MGTA, written nicely, where at the end there is a sensitivity study, and you could see the part acceptance rate influence on the sustainability on that specific case. And you can see that the lower your part acceptance rate, the higher your CO2 emission was. So there is a clear relationship. And I think that's the point I want to bring to engineers, is every single decision they make on how they want to learn or how they want to approach their engineering problem has a direct consequence on their environmental footprint. And I think that's the mission of 1000Kelvin from a sustainability perspective. We want to really hammer that message so that even engineers who are not generally connected to I don't want to say not all of them, but we don't think about sustainability when we make our decision. We think about productivity, cost, success. And I think this is something we want to integrate to that decision-making process.
So move to Scandinavia if you can and make use of the hydroelectricity. If you can't, then have a look at the data.
Be careful. Yeah. Be careful. Just try to minimize as much as possible. And I think, these are... I think it's our responsibility all, not only to promote additive manufacturing, because there is an opportunity for AM to be one of the most sustainable process, but besides AM, it's just a common sense approach that we need to integrate within the engineering communities going forward.
Yeah, absolutely. Well, thank you very much for talking with us today.
Thank you.
Any closing comments or things that we missed that you'd like to add in?
Well, first of all, thank you and to Gemma for inviting me. Great opportunity to chat. And number two is, I really think that serious people like yourself are needed to promote the message of sustainability in manufacturing. And I thank you for taking that mission.
Thank you very much.
Thank you, guys.
Cheers, Omar. Bye.
Cheers. Bye.